Imagine you're trying to provide Wi-Fi for a park. In a simple world, maybe the park only has 5 benches where people actually sit. Covering those spots is easy. You just buy 5 routers, put one at each bench, and every guest has a signal. Because the number of locations is finite, the solution is straightforward. But an entire theme park is a continuous space. Between any 2 points on a path, there are infinitely many specific locations where a guest could stop to check their phone. Does having an infinite number of possible locations mean you need an infinite number of routers to guarantee that every square inch is covered? This is the problem addressed by a property called compactness. It's a tool used in topology, the study of shapes, to understand how different spaces are put together. Compactness looks at these infinite, continuous shapes and asks if we can treat them with the same simple rules we use for small, finite groups of points. It's a way to see if an infinite space is small enough to be manageable. To understand this, look at the Wi-Fi signals. In math, a collection of overlapping zones like these is called an open cover. They are considered open because they don't have hard, jagged walls. Their edges are soft, allowing them to overlap and blend into the signals next to them. In a purely endless space, you might actually need an infinite number of these signals to make sure there isn't a single dead zone left behind. But if a space is compact, we get a guarantee. We are promised that we can take that messy, infinite collection of signals and thin them out until only a few are left. Watch as we clear away the extras. We can remove the redundancies until we're left with a finite subcover, a specific, limited number of zones that still completely blanket the area. If a space is compact, you'll never be stuck needing infinite resources to cover it. A finite selection will always be enough to get the job done. We can also see this by looking at the terrain of the park itself. Imagine we're building a continuous roller coaster track that runs from one side of the park to the other. On a compact space, any continuous line has an absolute highest and lowest point. This is the extreme value theorem. If not compact, the track could avoid a peak by stretching up forever, never reaching a maximum. Or the space could have a missing hole exactly where the peak should be. The track gets closer and closer to that height, but because that coordinate is missing, it can't actually touch its own maximum value. Compactness prevents these issues by requiring the space to be bounded, meaning that it doesn't stretch to infinity, and closed, meaning it has no missing points. These 2 rules keep the behavior of the space within strict limits. We can also see compactness through movement. Imagine a guest walking through the park, leaving a trail of glowing footprints, forming a sequence of points. If the guest were in a void that went on forever, those footprints could travel in a straight line, heading further away until they disappear. But because our park is compact, bounded and closed, the footprints are trapped. There is no away to escape to, and there are no holes to fall into. Since an endless number of steps are being crammed into a limited area, they eventually have to bunch up. They will cluster infinitely close to at least one specific spot, a behavior mathematicians call sequential compactness. In a compact space, every endless journey is eventually forced to settle down and approach a destination within that space. We've seen 3 different ways this works: infinite signals becoming a finite few, curves being locked between a peak and a valley, and endless steps being forced to cluster together. These aren't just separate rules. They are all different ways of describing how compactness keeps infinite scenarios grounded. Without these rules, infinity can be impossible to calculate. It creates endless voids and missing data points that leave questions unanswered. But when a mathematician identifies a space as compact, they know they aren't dealing with a runaway void. They know that no matter how complex the reality is, they can find a finite, logical answer.